1909, Rutherford told about the divisible units composed of positive charges concentrated in the nucleus with negative charge. Since some of the alpha particles are deflected to certain angles, it means that there is positively charged mass present in an atom. The number of protons or the number of electrons present in the nucleus is equal to atomic number. Hello everyone, welcome back to the session for the chapter Structure of Atom. Last class we have seen this content, that is Introduction to Atom, discovery of electron, charge to mass ratio of electron, discovery of protons, the characteristics of the positively charged particles, discovery of neutrons and properties of fundamental particles. Today we shall discuss about the topic of atomic models. In that, Thomson model of atom, Rutherford model of atom and representation of an element. We'll see first. See, these are the atomic models what we are discussing for our syllabus. Why atomic model has been started up means for to explain the distribution of electrons in an atom. So first, Democritus, that is Indian and Greek philosophers, told atom is very tiny, hard and uncuttable in the 400 BC. They told atom is the fundamental building blocks of matter. So it cannot be divided into further. Next, John Dalton in 1803, he told atom is a solid particle and indivisible sphere, means it cannot be divided into subatomic particles or it cannot be destroyed or it cannot be reconstructed. Next, in 1897, J.J. Thomson made an experiment that he told atom is a sphere of positively charged containing few negatively charged particles called electrons. So what he told, in a positively charged species or sphere, negatively charged species, that is electrons are present and distributed over it. But he could not tell about the nucleus. So next, 1909, Rutherford told about the divisible units composed of positive charges concentrated in the nucleus with negative charge. What he told, how the nucleus is present and how the electrons over it distributed around the nucleus, he told. He first founded the nucleus. He discovered the nucleus. In 1913, Niels Bohr, he told the concept of electronic shells. That is, how the shells have been distributed, and also electrons in atom are restricted to certain circular orbit. That is what we are telling, electron shells. Next, in 1926 and the present, what we are following today, that is Schrödinger equation. He founded about the orbital concept. And what we are today, we are reading about quantum mechanics, about his wave equation. From his wave equation we are following today. According to our syllabus, Schrödinger wave equation only we are having with some atomic properties with quantum mechanics. Okay. Now we are following John Dalton's and J.J. Thomson atomic model and Rutherford and Bohr's atomic models. First we will see Thomson model of atom. Okay. What he did, J.J. Thomson proposed that an atom has a spherical shape with a radius approximately 10 to the power of minus 10 meter. Means very small radius, that is, he considered that atom is in spherical shape. Okay. In this, positively charged is uniformly distributed. What he told, in the spherical shape of atom, positively charged species are uniformly distributed. The electrons are embedded into it to give the most stable electrostatic arrangement. How it was arranged means the electrons which are negatively charged species, it was arranged with the stable electrostatic arrangement with the protons, that is positively charged species. Next, this model we can tell that another also in another name, that is plum pudding and also a watermelon concept. Why we are calling as watermelon pudding concept means, when we cut the watermelon, we will be having a red color part will be designated or resembled as a positive species in the watermelon, in an atom. Okay. Next, within that watermelon, you will be having black seeds. That black seeds will be, we have to assume that black seeds are the electrons present in the positive charge species. So watermelon resembled the concept of the spherical shape atom. So he told the watermelon pudding concept for this J.J. Thomson atomic model. So an important feature of this model is that mass of the atom is assumed to be uniformly distributed over the atom. Means the mass of complete atom is uniformly distributed over the complete atom. Okay. See, this is exactly what he told. This is the spherical shape of atom having radius 10 to the power of minus 10 meter, and whatever this orange color part is there, that is positive charged area, and whatever the negatively charged species are there, that is electron. And how it has been arranged? With the stable electrostatic arrangement. Okay. And some of the limitations also there about the J.J. Thomson atomic model of atom. What is that limitation? It failed to explain about the stability of atom, because his atom failed to show how a positive charge holds the negatively charged species. Means what we have seen in a previous slide, that is how the spherical shape, within that spherical shape, how the positively charged species are hold up the negatively charged, how the bond has been made up between that, he could not explain. So the stability of atom he could not explain further, and he failed again for to explain about the nucleus also. He could not explain about the nucleus, and he didn't discover the name for nucleus also. So this is about the J.J. Thomson model of atom. Next, we'll see Rutherford's nuclear model of atom. What he did? He did alpha scattering experiment with his students. So what is that mean? A stream of high energy alpha particles from a radioactive source was directed at a thin foil of thickness approximately 100 nanometer of gold metal. What he did? He took a gold foil here, and by the alpha particle emitter, this is beam of alpha particles, he directed to the golden foil. Okay. This golden foil is having the thickness of less than or approximately 100 nanometer. Means very thin it is. A thin gold foil had a circular fluorescent zinc sulfide screen around it. Whatever this circular shape screen is there or material is there, that is fluorescent screen. Here they have used zinc sulfide fluorescent material. Okay. Next, whenever alpha particles struck the screen, a tiny flash of light was produced at that point. Whenever the beam of alpha particles are directed towards the golden foil, it projected here and hit to the fluorescent material. This spark have been noticed. Okay. So many spark have noticed on the fluorescent screen. This is the experiment. Next, we'll see the observation. What he observed from this alpha scattering experiment. So, most of the alpha particle passed through the golden foil were undeflected. Means, whatever the alpha particles passed through the atoms were undeflected. Means, it was in a straight line. A small fraction of the alpha particle was deflected by small angles. Whatever the alpha particles was deflected, that was in a small angle. Very small angle it was deflected in a small fraction. A very few alpha particle, that is 1 in 20,000, bounced back, that is were deflected by nearly 180 degree. Okay. In 20,000, only one or nearly to one can we see that is bounced back when the alpha particles have hit to the golden foil. It is very less in number, but when it bounced back, it will be around 180 degree. Okay. Here we can see that this is the nucleus. First point what we have seen, alpha particle pass through the golden foil, that is undeflected. See, this is completely undeflected, and when hit the entire mass, it is deflected. Some of that means in 20,000, 1 or 2 will be bounced back. See here, completely bounced back, that is around 180 degree. Okay, these are the observations what we have seen from the alpha scattering experiment. Then we'll see the conclusions. Okay, since most of the alpha particle passed through foil undeflected, it means most of the space in an atom is empty. Means what he told, whatever the alpha particle have been passed through, the atom, it was undeflected. That means the space in an atom was empty. The space completely was empty. So the alpha particle, whichever the alpha particle was moved from the atom, is straight or undeflected. It doesn't show the deflection. Since some of the alpha particles are deflected to certain angles, it means that there is positively charged mass present in an atom. So many alpha particles show certain angles. It means some of the positively charged mass present in atom. See here, small deflection have been seen, and also so many deflections. Here some of these small deflection have been seen. So he told that here positively charged species is present in an atom. Later, since only some of the alpha particles faced large deflections, the positively charged mass present in an atom has occupied very less space. Whatever the large space it has been seen here, large deflection, it occupied very less space in an atom. Okay. So, next point, strong deflections or even bouncing back of a alpha particle from metal foil were due to the direct collision with positively charged mass in atom. Whenever it bounced back, see here, completely bounced back or turned back. Why it has been turned back? When alpha particle have been hit to the central, completely positively charged species is present in center, so it has been turned back or bounced back, and this alpha particle had felt the collision with that positively charged species, so it has been bounced back. These are the conclusions of this experiment. So how he took the results of this experiment or conclusions? So completely he gave some statements after this, conclusions, observations, everything. What he did? The positive charge and most of the mass of the atom was densely concentrated in the extremely small region. This is very small portion of the atom was called nucleus. See, in this you have seen the very small densely positively charged containing species is in present very small region. That region we will call it as nucleus. Okay. Next, the nucleus is surrounded by electrons that move around the nucleus with a high speed in a circular path called orbits. This is nucleus having positively charged species in very rich and in a small region. So, whatever the orbitals surrounding the nucleus containing electrons called orbits. These are electrons and these are orbits. These are the circular path where the electrons will surround the nucleus. Next, electrons and the nucleus are held together by electrostatic forces of attraction. How these electrons and nucleus have been held up? These electrons and nucleus will be held up by electrostatic forces of attraction. These are the Rutherford's nuclear atomic model. Next, we will see the drawbacks of Rutherford atomic model. After doing this observation, conclusion and giving so many statements of the nucleus and orbits, then also he failed with some drawbacks. Why he has been failed, we'll see now. That whatever the alpha scattering experiment he made, it cannot account for the stability of atoms. Whatever the atom he is telling, having a rich species with positively charged atoms, electrons will be moving surrounding it, but he could not explain the stability of atoms. The model does not give any information about how electrons are distributed around the nucleus. See, we have seen the orbits, but on what context the electrons are moving around the nucleus, he could not explain. And another point is there, that is according to electromagnetic theory of Maxwell, that is according to electromagnetic theory of Maxwell, what he told, when an electrically charged particle moves under the influence of electrostatic force, it loses energy in the form of radiation. When a charged particle, electrically charged particle, when moving around the nucleus or under the influence of electrostatic force, it will lose energy in the form of emitting radiation or electromagnetic radiation. At that time, what it will do? It will fall into the nucleus and it will collapse inside the nucleus. See here, this is electron and this is moving here, okay, in a circular pathway. How the electrons will move around the nucleus? In a circular pathway, what we have called in orbits, it will be moving. Electrons are negatively charged species, so it will get accelerated. After getting accelerated, it will be moving in a high speed. It will lose energy or it will radiate some radiations, emit some radiations, so it will be moving on. After losing its energy, it will come towards the nucleus and fell into the nucleus. So, he did not explain the how spiraling of an accelerated electron into the nucleus will be happening. So, these are the three important points he could not explain in his atomic model, that is Rutherford's atomic model. So, he failed with this experiment. Next is atomic number. So, what is atomic number? The number of protons or the number of electrons present in the nucleus is equal to atomic number. Yes, the number of protons present in the nucleus is known as atomic number. When we will tell the number of protons and number of electrons are equal, then when we will tell means the element should be in neutral, means there should be no charge on it. That time we will tell the number of protons and number of electrons present in the atom is equal. How the atomic number will be designated? That is capital Z. How we have to be calculated? Atomic number is equal to number of protons in the nucleus of an atom is equal to number of electrons in a neutral atom. What I said now? Before, the number of protons and number of electrons will be equal when neutral atom will be present. If it is any having charges, then it will form a cation or an anion. Okay. Next, atomic mass number. It is defined as the sum of total number of protons and neutrons present in an atom. Means sum of total by adding of number of protons and number of neutrons in an atom, we will get the atomic mass number. How it will be designated? Capital A. That is, mass number is equal to number of protons, that is atomic number, and number of neutrons will be designated as small n. We will see the representation of an element. See, where x is this x is an element or an atom. Okay. This A is mass number, Z is atomic number. Okay, we have to be right like this way only. Mass number should be over, atomic number should be below. Example, if we get carbon, that is 6, 12, okay. See, this is atomic number and this is mass number. This is Z and this is A. Okay. So, the protons and neutrons present in the nucleus are collectively called as nucleons. What we will call? The protons and neutrons present in the nucleus, overall by collecting both, we will call it as nucleons. Now, let us see the problems. Calculate the number of protons, neutrons and electrons in the given atom. So, we have that is Z equals 35, atomic number 35, mass number 80. Atomic number means number of protons and atomic mass is number of protons plus neutrons. Okay. Since species is neutral, neutral means we doesn't have any charges on the atom, that is negative charge or positive charge, it doesn't have in that atom. So, the species is neutral. So, we are considering number of protons and number of electrons are equal, that is atomic number is equal to number of protons and number of electrons, that is 35. And mass number, number of protons plus number of neutrons. So, we are to find out what is the number of neutron in this. Atomic mass 80 minus 35, that is proton, we will get 45. Then number of protons is 35, number of neutrons is 45 and number of electrons is again 35. Okay. We will see the next problem. The number of electrons, protons and neutrons in a species are equal to 18, 16 and 16 respectively. Assign the proper symbol to the species. Here they have given the numbers. We have to write the respective atom to given and these numbers should be equal or balanced to that atom. Okay. The atomic number is equal to number of proton. We know that is Z is atomic number, that is equal to 16. Okay. And atomic mass number is number of protons plus number of neutron. Here number of protons is 16. See here protons, this is protons and respectively this is 16 protons. Number of neutrons, this is neutrons, this is also 16. This is electron and proton and neutron. Now we are adding up with proton and neutron. Okay. Now we are adding up proton and neutron, that is 16 and 16 equals 32. The species is not neutral as the number of protons is not equal to electrons. How much electrons we are having? We are having 18 electrons. Protons 16 protons. So this is not equivalent. So we are having 2 extra. Okay. It is an anion with charge equal to excess electrons, that is 18 minus 16 is 2. Symbol, what we are getting? This is sulfur, 32 is mass number, 16 is atomic number, minus 2, whatever this is, a charge given to this sulfur and this consider I have represent the anionic species. Okay. Next, we will see about isotopes and isobars. What is then isotope? Atoms of the same element with same atomic number but different mass number. See here, atoms of the same element, same atomic number but different mass number are called as isotopes. Let's see the example. Atoms of the same element, here also hydrogen, 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 same element, same atomic number. See 1, 1, 1 are the same atomic number. We are having different mass number, that is here 1, here 2, here 3. These are the isotopes of hydrogen. But different isotopes are having different names, that is protium, deuterium and tritium. These are the names of isotopes of hydrogen. Okay. How the atomic mass number or isotopes have been arrived means, see here atomic numbers are same but atomic mass numbers are different. So, how it has been arrived means, neutrons will be different. Here see the neutron is 0, here 1, here 2. How you will calculate the neutron? A equals mass, neutron will be P plus N, this is atomic mass, neutron will be A minus P, right? Like that when we calculate these things, we can get 0, 1, 2, different in neutrons. Similarly, atoms will be same, that is carbon, same atomic number, all are having 6, but different in mass number 12, 13, 14. The neutrons will be 6, 7 and 8. Difference in neutrons. So, like this isotopes have been came across, and also we can tell that the definition of isotopes. Next is isobars. Atoms of the different element with having same mass number but different atomic number is called isobars. Okay. So, we are having different atomic number with different atom. By seeing the different atomic number itself, we can tell atoms will be different, because the atomic number will be not same for any another second element. So, by seeing the atomic number differently, we can tell element also different but having same mass number. See here, carbon, one side 6 atomic number, another side nitrogen is having 7, but both of the mass is having same, that is 14. Okay. By this we can conclude this session, and next session will see these contents, that is Bohr's model of atom, electromagnetic radiations and electromagnetic spectrum. So keep watching our channel, and thank you.